All right, now we're going to start lecture 9, what will be Tuesday's lecture on system analysis of thermodynamic systems. Today we're going to introduce a new state function called enthalpy, and we're also going to introduce the term heat capacity, and in describing heat capacity we're going to constrain our definitions in terms of constant pressure or constant volume. Each case is going to use our state functions of either enthalpy in the case of constant pressure or internal energy in the case of constant volume. So let's get going. First, we want you to recall that work and heat are path functions, right? Work defined by W or W prime for non-mechanical work, heat defined by Q. If I have a capital Q, I'm describing, capital letter in general, I'm describing extensive property. And in each case of work and heat, we're really just describing energy crossing the system surrounding boundary, which is what makes them path functions and not state functions. I have W prime up there because I want to remind you that we are talking about more than just classical pressure volume mechanics. We are going to be able to use non-mechanical work extensively in this class, and enthalpy has a tight connection with that. Now, again in reviewing, we also know that there are three major system constraints that we describe. An isolated system, in which case neither mass nor energy can cross the boundary. We have very few systems like that in EME 301. That would also be called an adiabatic system. We have closed systems where we have no matter exchange but energy exchange happening across the boundary, and of course open systems where matter and energy exchange across the boundary. So today we're doing systems analysis on both closed systems and open systems. Let's start with the closed system. We're going to analyze the first law, the energy balance from the left side of the equation to the right side of the equation for closed systems. I'm going to start with integral balances. I'm going to start with the integrated form of a change in the system energy on the left side equivalent to a change in energy crossing the system surroundings boundary. Now, if I'm going to change the system energy, I'm going to be describing a process. So I'm going to have a delta U on the left side of my equation. And in this first offering of the energy balance, the first law balance, we've got the internal energy change as well as the external macroscopic changes from kinetic energy and potential energy. On the right side of the equation, we've got those path functions Q and W. Okay, that's equation 2.12a on page 56. Now, the note that I've got here is we're not writing a delta W or a delta Q. It's just not the standard way of doing this because the term such as work W already means energy transform. So it's already embedded into the meaning that is the case. Whereas on the left side, the change in state functions, we always put a delta in front of them. So that's a conventional way of writing these in the integral form. In the case of most of this class, we're going to take out those external energy forms. And we noted this is actually in your reading. We're basically simplifying our analysis by neglecting the macroscopic kinetic energy and potential energy changes from external fields, like the gravitational field. And so you end up with equation 2.13a, where we have a change in state, delta U, which is due to a change in properties only, which is why we call it a state function. A state function is a function of the variables, the measured properties, the measured or calculated properties. And on the right side of the equation, we've got heat and work. And again, I'm simplifying this right now to not include non-mechanical work, just so that we can build the analysis in its most basic form. So that was the integral version of the first law analysis for a closed system. Now if I do that same analysis but in a differential form, I'm going to have du is equal to that curly d q plus curly d w, or the inexact differential of heat and the inexact differential of work. You'll notice that all of the values, or all of the symbols, are capitalized, suggesting that they're all extensive variables, and that's going to make them all in terms of energy units, in this case joules. If I look at this as an instantaneous change with respect to time, a du dt, then on the right side of the equation you're going to see q dot and w dot, which is a shorthand way of saying the rate of change dq dt or dw dt. But it's still going to be an extensive representation, but it will be a rate of change, and so the units will be watts. Okay? And that is the basis for closed system analysis. There's no mass exchange, and we could add non-mechanical work or the instantaneous change of non-mechanical work, and we will do that later. But essentially it's showing that the change in the internal energy of the system on the left is going to be due to energy changes, energy transformations that are happening as energy passes the boundary between the system and the surroundings. Next up, we tackle analysis of the first law for open systems. Okay, now this is much more interesting. Now we allow mass flow to happen. And so I've got mass flow written in a mathematical representation of dm, m for mass, with respect to time. I'm going to focus my analysis on the system, and that will be the sum of mass flow rates going in for any number of different chemical species. Could be carbon dioxide plus oxygen plus water vapor for all of the inputs, and I need to know all the rates going in plus all of the rates of those species going out. Okay, so the summation is for different components in the system. The mass flow rate will follow the rate of them entering and exiting the system. In this class, you see quite a bit of notation where we are either in a molar framework or in a mass-based framework, per mole or per kilogram. In this case, we want to point out that mass can be converted over to moles as long as we know the molecular weight of the materials, or an estimate of the molecular weight for bigger materials. So you find that description, that analysis, on page 60. Feel free to go back and review that. But the mass out is going to be in terms of kilograms per second. And now I want to do a conversion of that data. I want to take that mass rate, that kilogram per second. I want to divide it by the cross-sectional area of mass flowing, say, through a tube. If we imagine mass flowing through a tube, it's going to enter a system. We've got a really nice diagram of that in this section. And I need to think about the cross-sectional area. I need to think about the specific volume of the material that is flowing in, right? And if I do a unit analysis, I find that I get velocity coming out of that analysis. Similarly, I can transform that so that the mass flow rate of the gas is the area times the velocity divided by the specific volume, which is equation 2.17. And I really advise you to go pull out your textbook and look at this while we're going through the video. From this, like why we took time to go to describe mass flow, is because we are introducing a new phrase called flow work. And flow work is really tightly related to that mass flowing in and out of the system. And we say this because it is the work that is done by the incoming fluid, because that incoming fluid is going to go into the system. It's going to be work done on the system to displace the fluid that is inside the system so that it can enter the system. So I need to do work to get fluid displaced and out of the system, or increased in pressure, or any number of different things. And the way that I describe that is as flow work. And so you're seeing here a description of that we find in page 61. Flow work, or the rate of work done by the flow of fluid into and out of the system, let's just use for one time, it's just the work going into the system, is going to be the pressure associated with the fluid going into the system times the mass flow rate going in times the specific volume going in. And so you see that there's pressure and volume together. We've got a mass flow rate times PV. And we already knew that PV was a type of energy unit that we would get for work. Okay? So let's take a closer look at how that works in an equation analysis. But flow work is going to be important, and I want you to kind of commit this idea of flow work to memory as we move along, because we will be talking about it in other lectures. So let's put that in equation form. We're going to use an integrated form, and I'm going to express that in extensive variables, so this will be a capital W. So this is the net work happening from fluid passing through a system. We're going to have something called shaft work, which you'll see in the diagram. It basically is, in this case, the mechanical work of the system that is not flow work. Shaft work plus the rate of flow work, and I'm going to have that mass rate times the pressure times the specific volume. You see that equation as Ws for shaft work plus the sum of all the different chemical components flowing in, right, expressed as the mass rate, times PV, which we already knew was PV work, but that is V hat, so that is actually going to be meters cubed per kilogram, and you're going to multiply that times kilogram, so ultimately you're going to end up with pure PV work. So this is first going to be the work done on the system, which is going to be positive energy input, energy going into the system, and then the second term is energy lost by the system. That is clearly energy and mass flowing out of the system, just according to the same positive and negative conventions that we've expressed for heat and work before. Okay. Now, at steady state, when we have a condition of steady state, we're at non-equilibrium, but the flow work is perfectly balanced. There is zero flow work happening, and I can express that additionally, that flow work, as a sum of mass times this term H. This H in, H hat in, and H hat out, which in thermodynamic language is going to be called specific enthalpy. So I've taken the equation right up here for shaft work plus mass flow rate times pressure times specific volume, and I've bundled together that PV term to include, or to be grouped together as something called specific enthalpy. And enthalpy itself is going to be that equation in the lower right. H hat, that's the specific enthalpy, or the energy per kilogram, is going to be equal to the internal energy, the specific internal energy, plus P times the specific volume. Okay? Which is saying I used this expression, this discussion of flow work, to introduce our new state function of enthalpy. So we have the state function of internal energy, and now we have a state function of enthalpy. Enthalpy is the state function that includes internal energy and flow work. Now that's pretty abstract, so I'd like to think in terms of how you would describe energy from internal energy and enthalpy. Well, internal energy is already the capacity to do work and exchange heat. Enthalpy is the capacity to do non-mechanical work and exchange heat. right? And I've got their release heat, but I mean exchange heat as well. So I do this diagrammatically right below here, where you see a line for H, and that the length of that line is basically going to be the specific energy of that line. And I'm going to have H, and I'm going to see that H is going to be defined as the sum of the specific internal energy plus PV work, where I have specific volume for V. The interesting thing here is that both H and U are state functions. And so H is a state function that also incorporates an additional factor that is not internal energy change. And when we think back of what three things can change internal energy, it was sensible heat, latent heat, and a chemical reaction, or an enthalpy of reaction. Boy, that word just popped in there, didn't it? But why don't we think about it as the heat of reaction as well? Okay? If we use the equation of state for the ideal gas, we're going to see something interesting. We're going to see that the relationship of enthalpy when expressed as an ideal gas is still going to be U is equal to PV. And the V is going to be the molar volume, but there's V over N. We know that that's a part of the ideal gas relationship, and so we can express it as the internal energy plus the ideal gas constant times T. In doing so, we've said that enthalpy is a function of temperature only for ideal gas behavior. That is exactly the same as for internal energy change. As a gas changes in temperature in an ideal gas setting, that will change the internal energy. That will also change the enthalpy. Now, we can take this information and we can form transient energy balances for the internal energy number 2. And really that's what we were going after. We wanted to kind of set things up in terms of work to describe how we're going to change the internal energy of an open system. We were trying to solve the first law for an open system, but we had to explain what is an additional form of work to get there. And in describing our additional form of work, we opened up a new state function. That state function was enthalpy. So let's describe that. You find it in equation 2.22. The rate of change of internal energy of a system, and that should be a lowercase u actually, is going to be the sum of the mass flow rate times the specific enthalpy minus the mass flow rate out times the specific enthalpy of the fluid going out, plus our heat and shaft work terms. And the enthalpy of that system should be in balance at steady state, and it accounts for the change in internal energy and the flow work in and out. Okay. Actually going to make a modification of this guy so that we have some consistency. Okay. So, the idea here is that if enthalpy describes both internal energy and pressure volume changes, we want to think back again, what is it that changes internal energy? And so we go right back to that first list in the beginning of the chapter, where we know that internal energy changes will come from changes in temperature, changes in phase, and changes in chemical structure from a chemical reaction. The focus of the end of this lecture is number 1. Oh, I did want to point that out. That's right. That third point is enthalpy of reaction. Remember, enthalpy of reaction is the capacity to do non-mechanical work. And chemical reaction is definitely a form of non-mechanical work. Okay, so let's go back to number 1. We're going to take a kettle of water, we're going to put the kettle on a hot plate, and we will change the temperature of that water from room temperature all the way up to 100 degrees Celsius. And we will do that by a change in sensible heat. We're going to have energy crossing the boundary, that would be heat, and it's having a sensible effect. It is making the molecules vibrate, wiggle, turn, and that will drive a change in internal energy. So we get a change in internal energy from a change in the property temperature, from temperature 1 at room temperature, that is state 1, to temperature 2 near boiling temperature will give me state 2. If I want to measure that water behavior, I use a piece of equipment called a constant volume calorimeter. That's one of the types of instruments that I can use, a constant volume calorimeter. And what it does is it tells me how does temperature change inside of a material for quantitative input of energy that I'm adding to the system or taking out of the system. So a calorimeter, it measures calories, excuse me. So, or it measures energy units, or it measures the temperature change per energy unit that we put in. And that leads us to talking about heat capacity. Sensible heat change, or the effect of the internal energy relative to sensible heat change, is described by heat capacity at constant volume. So if I have a constant volume system, let's suppose that I have a pressure cooker, or let's suppose that I have an egg that I'm boiling, where the inside of the egg is a constant volume clearly. So I'm going to write something, heat capacity is going to be a lowercase c, and it's making sure that we know that this is an intensive variable, and it's got that lowercase v which says at constant volume, and I've got the 3 lines there that says this is a mathematical equivalence. Just like we started defining temperature as temperature is equivalent to the partial change in internal energy relative to the partial change in entropy at constant volume. Now we're going to describe the constant change of internal energy with respect to the constant change in the partial change in temperature. Let's try that one more time. The partial change in internal energy per partial change or instantaneous change in temperature at constant volume. Now, when I have this condition, the system is closed, and the system is at constant volume. Again, I've got basically a pressure cooker. No matter can go in and out, but energy can go across the boundary. So all energy going across the boundary is heat. There's no work here. It's just heat going across the boundary, changing the internal energy of the system. On the right side of the equation is only heat is changing the system. Work is 0, and the internal energy is changing, and I can express that through equation 2.23 because I have du equal to q. Turn that from an integrated form into a differential form, and I'm going to have partial u is equal to dq. So I'm going to have dq over dt is the measured way of describing the heat capacity, the volume constrained heat capacity. And I'm reflecting changes in energy transfer across the boundary per change in the temperature of the system. What you'll see in looking at your figures in the textbook right next to this equation is that we're actually describing a slope. Now, Q is going to be a unit term of joules. If I have lowercase q, it's going to be joules per mole. I'm dividing that system by temperature units, or Kelvin. So my unit analysis will give me joules per mole Kelvin. The basic question here is what else out there in thermodynamics land is closely related in unit analysis to heat capacity? So what do we have out there that is joules per mole Kelvin? And what we find is that entropy has joules per Kelvin, or molar entropy is going to be joules per mole Kelvin. So entropy describes the dispersal of energy. Heat capacity must have something similar to do with the way that energy is dispersed in a system. And I just want you to keep that in mind as we move along forward in the class. Now for you, I've got a task. I'd like you to review figure 2.10 on page 68. That's associated with these equations, and it's going to be for the constant volume system, and for what we've got coming up, the constant pressure system. So just a task for you. Go in, analyze that figure along with this video. I'm going to take now a new constraint on my system for heat capacity, constant pressure. A constant pressure system for heat capacity is going to be Cp. And Cp is also going to be defined, but it's going to be defined as the equivalency of a partial change in enthalpy with respect to a partial change in temperature at constant pressure. And in a closed system, dH is equal to Q, so that I can arrive at equation 2.29, where dq dt is going to give me the constant pressure heat capacity. In either case, all I need is to measure the energy across the boundary. I will then specify whether it is a constant pressure heat capacity or a constant volume heat capacity based on the conditions of the system that I'm analyzing. So here we go. Constant pressure. Where do we find that? Constant pressure systems? Well, they're all around us. They're very common in cooking and in baking. When I'm baking a cake, the surrounding atmospheric pressure is constant. The atmosphere around us, the chemistry existing in the atmosphere, is also existing at constant pressure. So we have lots of scenarios with constant pressure systems where enthalpy is going to be a big part of our equations. And you see how enthalpy is linked with constant pressure constraints. Enthalpy will ultimately drop in a lot more often, so it's worth knowing why this is such an important second state function. Now, in your analyses, in your problem solving, if you go into the real laboratory or you actually are trying to solve a problem mathematically, you want to look up values and coefficients for solving heat capacity, and we find those values and coefficients in in Appendix A, tables A2.1, 2.2, and 2.3, where they break up the materials into their different kind of phases. But you already know one. You should know one very well, and that is the heat capacity of water. Under normal atmospheric conditions, that's going to be 1 calorie per gram per degree Celsius, or 4.186 joules per gram per Celsius. I put that in there because it's so common. We do so much with water. We should know about a general heat capacity term. Now, the last thing I want to leave you with is if you look up heat capacity and hyperphysics, that's the webpage from, I believe, Georgia State University. They show, in addition to showing some nice supplemental educational material, they've got a great description of the molecular model that was formed by Einstein, built off of the Debye model. So it's the Einstein-Debye model for heat capacity. And very simply, when we're describing heat capacity, we're describing it as a sum of two parts. The heat capacity total for a material is going to be the electronic contributions to the heat capacity, or the way that electrons are moving through the material will affect the way that energy changes with temperature change. And then we add to that the vibrational changes, the vibrational heat capacity changes, which are going to be the vibrations of the lattice of a crystal, which we would call phonons, or just the vibrations happening in a fluid. So if I have electronic contributions and vibrational contributions, collectively, they will contribute to the total heat capacity. And electrons zipping around and bonds that are vibrating and twisting and bending are really describing the way that energy is dispersed in a system. So once again, we come back to thinking about energy dispersal, which is entropy. So there is this close link between heat capacity and entropy, and I'm just kind of talking about it a little bit just to keep your mind on it. But otherwise, I think we'll take a rest. Thank you for your time, and we'll see you next lesson.